Thanks everyone for joining us for today's speaker series. This month we're hearing from Alex Webster, who's a faculty member in the TN at UNM. Alex, I'll go ahead and turn it over to you. We're looking forward to hearing about your research.
Thank you. Let me just go ahead and share my screen. All right. You all see that? Great. All right. Thanks so much for having me, everyone. I'm presenting this work. This is a manuscript that's been in development since the very beginning of the TN to help us start to work on frameworks for doing some of the convergence research that has been talked about in previous sessions. And my co-first author on this paper is Yolanda Lin, who can't be here today, but I want to acknowledge her, as well as the author team that you see here. These are the people from the Transformation Network and from departments all across UNM that helped facilitate the testing of and development of this framework, and have been the ones that stuck through from deep in Zoom lockdown land to the submission of this manuscript in, what was that, January. So I really appreciate them, and I'll talk a little bit more about them as I go on. Okay, so the context for this work in the Transformation Network, like a lot of our work, is that billions of people and a lot of critical ecosystems rely on managed water resource systems. So by managed water resource systems, I mean systems that involve the storage and transport of water through some combination of what I'm showing you here: the seasonal snowpack, constructed reservoirs, groundwater aquifers, lakes, rivers, aqueducts, pipes, all of those things, which is a combination of things that are done by human activities as well as hydrologic processes. And these systems are really designed to buffer human communities, and in some cases, ecosystems from hydrologic extremes like drought and flooding. So a dam, for example, is going to both buffer downstream communities from drought, as well as, a big flood pulse that might overtop by creating a place for that water to be stored. But the thing is that's being increasingly acknowledged is that a lot of these contemporary water resource systems that we have today were designed, especially in North America, for a more wet and stable climate than what we have today. This is the classic example of why the Colorado River Basin is super overdrafted, because all the water rights that are kind of the less infrastructure-based parts of these water resource systems were based on a time where we had more water. And same with these dams and aqueducts, to the point where people are seeing that if we can draw down our reservoirs that were built for the capacity for larger and more stable hydrologic systems, that we may not have the ability to reach the intake valves for some of these, for example. That's something that's happening here on the Rio Grande. But now we see that climate change, shifting land use, and that rising water demand are diminishing the buffering capacity, like I was just explaining. And so we really need to adapt these water resource management systems to these new conditions that are getting increasingly acute. But the complexity of doing that is something that people are really still managing or grappling with. And that brings me to the idea that has been stated that water resource management, broadly speaking, is what is called a wicked problem. Wicked problems, this idea was articulated first by some folks in the early 70s. It's the idea that it's a problem with many uncertainties and risks that lack a clear path or a point of resolution. So in this figure, they're showing a non-wicked problem of something like a homework assignment where we know what the right answer is and the solution is possible, and there's clear guidelines and rules, and there's one answer. And a wicked problem, in contrast, something like water resource management, There's a lot of possible solutions and no chance to learn from mistakes. So you're applying it to a complex system such that you can't undo what you've applied a lot of the time. And that makes things really messy and unclear. And people get really stressed about this. I do like to take an optimistic approach that the nature of wicked problems of having multiple paths towards multiple forms of resolution can actually be viewed as sort of an opportunity, because if we can identify those paths and points of resolution and agree upon them, then that provides more options for solutions. This is something that is related to the guided transformation approach in the transformation network that Mindy and others have talked about in previous speaker series. And that brings me to mentioning our convergent research approach in the transformation network. So the first talk in this series by our fearless leader, Mindy, articulated this in depth. And the application here is that the idea of a wicked problem like water resource management, a major barrier is effective integration and co-production of knowledge across and beyond our academic disciplines. And this is something that Convergence Research is really trying to address in the themes and in the traditions of multidisciplinary work, interdisciplinary work, transdisciplinary work. And Convergence Research is kind of the new buzzword on the scene. And the Transformation Network is figuring out what we uniquely want to bring to that approach and how we want to articulate it. And so as you can see here, systems thinking is one of the Transformation Network's core approaches for achieving our convergence research. And so I want to describe systems thinking and how it applies to this problem of wicked problems in a little bit more detail. And forgive me that if you did attend Mindy's talk on this, this will be a little repetitive, but I think it's really important for me to talk about the history of systems thinking a little bit in order to give context for the approach I'm presenting today. Okay, so systems thinking is a body of theory and practical applications that aims to infer how systems behave by gaining a really much deeper understanding of their underlying structure. So in this definition, I'm showing you here, a system is defined as a collection of interconnected elements that generate behaviors over time. And this idea of using systems thinking in the transformation network as part of our convergence research approach has been something that myself, Yolanda Lin, and Jan Bol have been working on, particularly as charter leads, but other folks in the network like Ryan Morrison, for example, have a lot of experience with this. So to get a little deeper, when I say models, that word can mean a lot of different things. A model can refer to any stylized representation of a system. So systems thinkers have been developing a constellation of modeling approaches to explore systems' underlying structures, everything from this kind of conceptual and quantitative to computational and quantitative. So a model is any stylized representation of a system. Systems dynamics modeling, I'll be using that term a lot, is one such set of approaches, and it really emphasizes the interactions of stocks. So here, for example, is an example of a stock and flow model where the stock is the water in a bathtub and flows, things that can make stocks increase or decrease. So the rate of draining from that, for example. So system dynamics modeling, as this example shows, is really intuitively useful for describing water resource systems, because water stocks, like a reservoir, for example, and flows like rivers are really key elements of those systems. But I want to make sure everyone understands that stocks and flows can be used to describe less physical elements, such as for example, something we explored in this work, the accumulation and loss of trust in a water management authority from members of a population, for example. Okay, so even with all this constellation of approaches, systems thinkers, like to have a lot of options. So they have a lot of approaches to meet those needs. So for example, this process inquiry modeling map, it depicts an organization that was facing a deep sense of stagnation. And this modeling technique is designed to explore patterns of dysfunction there. Okay, so as a field, systems thinking has gone through several kind of paradigm shifting waves. And I think it's really useful to understand this history a little bit, to understand the current state of the field and its limitations for convergence research in the transformation network and on water resource systems. So starting in the 1940s and 1960s, early users of systems thinking really broke down barriers between conventional academic disciplines by generalizing unique modeling traditions from those different disciplines into a common set of practices, which is what a lot of those models that I was just showing you involve. At this time, we're still really emphasizing quantitative models that are meant to be representations of reality. And they kind of would set really strict definitions of the boundary and the scale of those models and the scope of the modeling product from kind of a top-down, expert-driven perspective. Then in the 60s and 80s, there was a push in the field to consider models more as aids for the development of understanding between different people with different perspectives, rather than strictly like a representation of reality. And this really led to the development of more quantitative or qualitative and conceptual approaches, like those stock and flow diagrams, but with less quantitative bases, and more of an emphasis for developing shared understanding on the meaning of that model behavior. But those scale and scope judgments were really set still in a top-down matter, and that really led to a third wave that emphasized acknowledging and critiquing how those judgments around scope and scale of modeling projects are made, particularly from the perspectives of more marginalized members of a system. And this third wave also embraced the idea of methodological pluralism, which seeks to take all those different quantitative and qualitative approaches to the first two waves to create more of a flexible and responsive systems thinking practice altogether. Okay, so there is a fourth kind of wave that's emerging now, and I'll touch on that more towards the end of my talk, because this is kind of where we're at right now. So when considering how to use systems thinking to address modeling and understanding water resource systems, we really felt like there's some important limitations of current approaches. So the first one is that there's a lot of collaborative approaches that were really developed to address those first and second wave critiques. But most of that collaborative modeling is still happening in a way that's really limited in time. So based on incentives like funding, for example, and trying to address a particular set of concerns, research teams kind of convene for a project only for as long as those incentives are present, and that causes models to really represent just a snapshot in time and a snapshot of a particular group of perspectives. And even though some of these collaborative approaches have continued for a long time, there's some really great examples, for example, in the understanding of Asakia networks in the Southwest. Even though those can occur in a long time, it's not formalized into the modeling process how the contributions of that long-term collaboration and evolving partnerships can change the outcomes and the model. So you're lacking a bit of what I described earlier as boundary critique by not really directly looking at how those kinds of long-term factors can change modeling and the ideas that emerge from these types of models. And I think particularly for the convergent approach and for the transformation network, both from a practical and a transdisciplinary perspective, it's really important to acknowledge the importance of how community partnerships evolve and get deeper and new ones get added over time, and that there needs to be a way to incorporate those evolving community partnerships into a systems thinking approach. And that, I think, is currently pretty lacking. Okay, then the second one is that Water resource systems are multi-scale across both space and time. We've got processes happening at fine spatial scales and fine temporal scales that are then influencing things happening on coarse scales and vice versa. And we really want systems thinking to reflect that kind of multi-layeredness, to accurately model the approach of the behaviors of the system, and really to preserve the relationship between the nuances that we see at fine scales and the abstractions that are necessary to model systems at coarser scales. But systems modeling methodologies now, as they stand, tend to, most of them, delineate a set scope and scale for practical purposes for a modeling project and go forward with that. And that really prevents the ability to consider that multi-scaledness. And together, those limitations, the limitation on long-term collaboration and the limitation on multi-scaled approaches, really affects the adaptability of these models. So the idea of adaptive approaches, we see it in frameworks like adaptive management and other ones, are really shown to be necessary to address how things are rapidly changing with climate change, with land use change, social dynamics, things like that, in water resource systems. So we know water resources and systems are experiencing change very rapidly, but that's currently lacking in systems modeling. So we really wanted to develop a new approach in systems modeling that drew on the strengths of some of those different paradigmatic waves, but that also addressed these issues that I'm outlining here that we think are especially important for modeling water resource systems. And this is what we came up with. So we proposed this new framework aimed at making that systems thinking collaborative on longer timescales, more adaptive, and more multi-scalar. So I'll walk through this now. So the framework has 3 levels across which models are organized. The first model in the blue here is one coarse scale level model that could contain a single conceptual model that describes major themes of interest within a water resource system and interrelationships between them. The second mid-scale level contains a set of system dynamics models that address more broadly scoped research questions and represent more intermediate spatial and temporal scales. And then this fine scale level contains a set of system dynamics models that address more narrowly scoped research questions and represent fine spatial and temporal scales. So we're depicting this as these 2 intersecting triangles, one with a broad base at the top and the other with a broad base at the bottom, to emphasize what I'm calling bidirectional hierarchy, which maybe you could just consider non-hierarchy or canceling each other out. But the idea is that it's hierarchical from the bottom to the top, if you see this arrow here, in that the scope and the scale of any one model increases in that direction. And then it's hierarchical from the top to the bottom in that the number of models needed to represent the water resource system increases in this direction. So this allows for flexible scope and scale issues, and it also allows for many models to interact with each other. So in terms of how to use this, we have recommended a middle out modeling approach. So multi-scale modeling exists in other fields, nanoscience, biology, things like that. And they have found also that a middle out modeling approach can be really helpful. And it's really preferable for both practical and kind of theoretical reasons that I want to note. So the first is that, where is it? Oh, I lost it. There it is. Is that you don't need, when you're starting a new project with a middle out approach, the detail that's required at a fine scale. And that can be really helpful when you're building initial research questions and discussions with community partners and whatnot, where you don't necessarily know what fine scale details you need. The second is that it's been shown that a bottom-up approach, especially in a complex system like a water resource system, can really miss the inclusion of emergent factors. You guys have all of these tiny little details that are coming together, but we know from complex systems theory that there's unique factors that emerge at coarser scales that you might not catch by doing it in that direction. And then the top-down approach, we as the modelers, along with our partners, we just have cognitive constraints to think about all of the possible complexity happening at a broad scope and scale. And that is a real limitation in systems modeling of dealing with it. And so starting at a coarse scale, you would very likely miss details. And so you can, by a middle out approach, kind of hedge your bets against all of these issues. Okay, so I want to get into how we are using this, but I want to show first and give a preview to kind of the ongoing modeling process. So within each of these, there is a set of processes embedded that guide the creation of those coarse and fine scale models and then encourage revision of models over time. And so I've generalized these in the figure here, but I'll provide some specific examples of how we do this in the rest of the talk. But I do want to note here that regardless of the exact tools that you use, these processes can cause the creation or the modification of models at any level of the framework and allow that change to feedback on models at other levels by initiating reevaluation and possibly reformulation of those models at those levels. Okay, so altogether, those three levels of modeling, we feel kind of balance the need for a flexible and interacting levels of different scopes and scales. So getting at that multi-layeredness, that adaptability, but also providing practical limits and tools to allow you to do the modeling and proceed with your work at each level instead of just getting paralyzed by the complexity of the system. And before I get into some examples, I want to mention that our Transformation Network student, Atlin Johnson, I don't know if he's on the call here today. I think he might be in South America, but he's creating the technical modeling architecture in GoldSim, which is a popular system dynamics modeling platform to allow places where models at these different levels can be plugged in and be able to interact with each other. So that's the basis of his master's that we're continuing to work on with him. Okay, but before we get there, we needed to provide Atlin with a bunch of stuff to work with to create that technical framework. And so we really wanted to test tools at these different levels within the transformation network and to begin to develop how we would practically use this. And so following the middle out approach, we started at the mid-scale system dynamics models. And we did this, we wanted to kind of jumpstart the testing of this framework by building models at this scale. And we needed a case study. And the case study is the Santa Fe watershed that is shown here. This is part of the Transformation Network's Rio Grande Fireshed exemplar that we're working on, or kind of integrative place of a lot of the work that we're doing that we started with here. And one of the big reasons why we worked here was that Courtney Flint and Leonard and Maury Hensley at the Santa Fe Watershed Association had been working there for several years to kind of understand the kind of social ecological landscape there and the factors that are influencing it. And they just published a chapter on resilience in this book, Resilience in Riverine Landscapes, that is a really great resource for understanding it. And I'm not going to go into all the complexities of the Santa Fe watershed, but the summary is that it's full of examples of these kinds of wicked problems of water resource management, but also on the more optimistic side, a lot of potential for guided transformation because of all the possible pathways to solutions. So I'm going to give some examples from this framework. I want to emphasize that we really wanted to use this to look at and test some of the tools in the system dynamics literature, and we weren't trying to create the model of the Santa Fe watershed. That was not the goal. This was a test bed for us to work out what tools are useful within this multi-scale framework. So we started with a workshop to jumpstart a research team at building those mid-scale models. And we utilized techniques for this from the group model building literature, which is a family of group facilitation techniques that are linked to computer models, that are system dynamics models, and developed within a group meeting setting. And we did this by doing a 6-day workshop back in 2021. And Koti Kramer, an undergrad at UNM at the time, attended the whole workshop and summarized everything we did into this beautiful figure here that I'm very appreciative of, because it summarizes a lot of information in a relatively concise way. So I will use this to walk you through some of the things that we did from the group model building literature to start with these mid-scale models. So on day one, we called this the day where we took ownership of the workshop. We were testing this workshop on a group of interdisciplinary faculty that were advertised through the Transformation Network and through people interested in water resources at University of New Mexico. And we got a group of people, students, faculty, researchers from all of these different disciplines that I'm showing you here. Though I will say this list doesn't reflect all the spheres of knowledge that participants identified with. And the one thing we did right away was we tried to understand and parameterize what people's relationship with the Santa Fe watershed was. So each of these yellow dots here was a dot that each of the participants placed on this pie chart that really looks at what the relationship between how affected the person is by dynamics in the system in the Santa Fe watershed, and then how much they are able to influence it. So as you can see, most of our participants were in this quadrant where they felt they had less influence on what's going on in the Santa Fe watershed and were less affected, with the exception of some of these people more close to the middle of the diagram. So this again really emphasizes that this was a group of people outside the watershed for the most part, and that we're looking at it from our kind of academic viewpoint. Okay, so then on day two, we kind of defined elements that were influencing the watershed. So participants brainstormed and defined the elements that they were interested in, and elements in a systems thinking framework are parts of the system that are in some way quantifiable and can change over time. So quantifiable is a loose term. As you can see, some of the elements here, this one, for example, was political will. And the most important thing is that you can imagine how it changes over time. So here they imagined political will of people with lots of resources would increase over time, and political will of people with few resources would decrease over time. So they sketched out these different, these are called graphs over time in the group model building literature, to kind of make sure that the elements that you're identifying have these dynamic structures. And they range from ones like that to the incoming stream flow into the McClure Reservoir, which is one of the reservoirs in the Santa Fe watershed. Okay, on day three, people broke out into small groups. There were 4 groups, and they looked at all of these elements of with their graphs over time, and they picked the ones that they found most interesting in terms of dynamics in the Santa Fe watershed. And then they tried to stick them together to produce a research question. So I don't have the combinations here, but you can imagine trying to understand how political will and McClure incoming stream flow are connected to each other. You can then, by discussing that in an interdisciplinary group, produce a research question related to that. And so that resulted in 4 research questions from the 4 interdisciplinary groups. The first one, for example, are what are the connections between trust and adaptive capacity in the Santa Fe watershed? Under what conditions does information and education increase water conservation or attitudes about water conservation? in the Santa Fe watershed? What are the natural controls on water that is available for natural systems, human populations, given climate change? And then finally, this one's a mouthful, but it's really interesting. How is policy change efficacy impacted by disconnections between information, knowledge, and behavior resulting from the failure to integrate Indigenous perspectives, deprioritization of relationships and trust building, and the resulting inadequacy of information and a holistic/inclusive knowledge development in the Santa Fe watershed? So that one, for example, was looking at what is the relationship between change of information, knowledge, and water conservation behavior over time, and then brought in these elements, these interacting elements like Indigenous perspectives. Okay, so then on day 4, they took those questions and started building a system dynamics model in a collaborative online cloud-based software program that I'm showing you an output of here from an example from one of those groups. So the idea was to create those stock and flow models where you were capturing important things that would address your research question. And then on day 5, everyone told each group told the larger group the story that they felt like that system dynamics model was telling them, or at least one of the stories. So this modeling framework allows you to draw it out and then actually simulate if you change one of the stocks, how that kind of cascades through the system and affects other things. And so by kind of exploring those simulations, they were able to tell some really interesting stories about how the influence of one thing influenced something down the line in the systems model in complex ways. And importantly, by telling these stories to each other, we were able to start to look at what the connections between the different between the different models were. For example, something that emerged in 3 out of the 4 models was the importance of trust in the Santa Fe watershed, the trust in authority and trust in water management authorities, and how that influences people's behavior around water use, conservation, things like that. Okay, so then on day 6, we did some reflection exercises, and we came up with a few things. We decided that this was really just the beginning. We were nowhere near effectively modeling the Santa Fe watershed, but that really fits into that idea of third wave systems thinking, that this is second and third wave systems thinking, that it's not really about representing reality. It's about hypothesizing dynamics, understanding what gaps in our knowledge are, and things like that. And so we also came away from that. It really highlighted to everyone that there were issues with the scale and the limitations of the scope of these projects, and that we both needed more specific models to get into some of the nuances and broader models to understand those connections across these different models that we were looking at. And that really, I presented it as if we came up with the approach first, but really it was that discussion that led to this multi-scale framework that we have since developed, where we wanted to be able to move up and down in scale in terms of the scope of the model and the number of models that we're dealing with. Okay, so once we got there, 12 participants from that workshop, including the 2 facilitators, which was me and Yolanda, continued to work together after, with the objective of getting to this core scale conceptual model and to work on creating more fine scale system dynamics model and testing what tools are useful to do those things. So the participants that went on from there represented a range of academic disciplines from biology, geoscience, engineering, geography, policy planning, social psychology. So not quite as broad as the original group, but still a pretty broad interdisciplinary group within an academic setting. And the first thing that we did was to try and define the course scale elements that we would work with. So we took all the different elements that were in all of those 4 models that came out of the workshop, plus more that were brainstormed and considered in the workshop, and we categorized them or sorted them into themes using a activity called card sort. That this, I'm just showing you the beginning of it. It took a long time because to get 200 plus into 21 themes was really challenging and required a lot of back and forth discussion. But once we got to what those 21 were, we then collaboratively built a glossary of exactly how to define each of those themes so that it was inclusive to all the elements that we thought were important in the Santa Fe watershed. And one offshoot of this was a related framework called fuzzy sets that Yolanda and I have another paper on that really was about like the even higher coarser scale conceptualization of those themes into social, ecological, and technological categories, and how we could kind of agree to disagree on how to categorize some of those within an interdisciplinary group like this. So then we took all of those 21 themes and we did what's called a structural analysis. And the purpose of this is to hypothesize and visualize the interrelationships of those elements. So every member of the team, the 12 members of the team, had to take a survey where they related how each of those 21 themes related to all of the other 21 themes, or how they thought they did, and then their degree of certainty around that. And that resulted in this spaghetti mess here of everything influences everything is basically the outcome of that. But the weight of these lines influence greater, stronger, and less strong influences according to the understanding of members of the team. So then what we did with that, because this is impossible to look at, is there within systems thinking structural analysis, there's this idea that different categories based on their depth of interrelatedness with other things fall into the categories that I'm showing you on the top here. So this is a novel contribution to this system of structural analysis that we created, where we took the categories that are understood from systems theory to relate to each other and created kind of a model template of how they're related to each other. And this model template really highlights exogenous versus endogenous versus core endogenous elements and their interrelationships. So exogenous elements are those relatively independent of the system that kind of condition it. Endogenous elements are those that influence by other elements in the system. And then core endogenous elements are those that are central to the internal dynamics of the system, that are very sensitive to everything that's going on in there. And we then were able to take that and take all of our factors and their interrelatedness and slot them into those themes to create that core scale conceptual model of how these different core scale factors are interacting potentially in the Santa Fe watershed. So for example, you can see in our core endogenous group, we've got water quality, quantity, and availability, probably not surprising for modeling a water resource system. Adaptive capacity was another one. And where is it? Social capital was one that was kind of on the margins between core endogenous and endogenous, but was really important. And that social capital was kind of our way of continuing to talk about that trust element that came out in the workshop models as super important. So there we go. We got our core scale conceptual model at the top. And what we would like to do going forward, we're here. Let's see here. We discussed our core scale conceptual model. We identified lots of new emergent questions. And the idea is that that can then be used to construct new mid-scale models to address those questions, new research questions, bring in new community partnerships, create new questions in order to get back into the middle of the triangle and then continue as that. So I can't go into every detail of that, I want to hit on the how we did the fine scale models. So Yolanda Lin teaches a system dynamics model or an environmental modeling class in geography that's cross-listed at UNM. Many of our students have taken it at this point. And in her first iteration of that class, she used it to have the students take those mid-scale models and develop those finer scale models down here. So we had, in the context of our class with these grad students, they discussed the mid-scale models and figured out what they could parameterize with data or have a deeper conceptual understanding of. Then they identified the issues of scope, scale, and nuances and uncertainties that are kind of inherent to that middle conceptual scope. And then they constructed fine scale models to address those issues with scope, scale, nuance, uncertainty, things like that. And then they were able to take those fine scale models that they developed, reconnect them to create new mid-scale models that we can then use to influence our course scale models in the future. So an example of that mid-scale model that's been revised is Yolanda student, transformation student Lindsay Roche did one on snowpack influences. This is a fine scale model in GoldSim that then was connected with other models in the class to develop new course scale models. Okay. That was a whirlwind. There's so much more that I would like to talk about, but I wanted to really emphasize the kind of set of tools that we're using and that we've developed protocols for and whatnot that other members of the Transformation Network can take advantage of. So I'll just end with some of the conclusions. So the authorship team looked over all of our results kinds of once we had that big picture and really discussed, was this exemplary of convergent research? What do we need to do next? And we came up with two broad conclusions. The first is that within our academic setting, we did think that the CAMS framework, the Collaborative Adaptive Multiscale Systems Thinking Framework, effectively facilitated convergence research on this water resource system within the limitations of our setting. And the thing that we really felt did this effectively was that this whole process developed metacognitive skills. So this is the idea that's the process of thinking about one's own thinking and learning. And it's considered really essential to conducting interdisciplinary research because it helps participants understand how other disciplines construct knowledge. So we spent so much time just trying to understand the language that each of us used and understanding our own kind of biases and the limits of our perspectives from our disciplinary training, and learned a lot about other people's training and how it influenced their thinking. But our other big conclusion was that bridging these disciplinary divides was an important first step for convergent research, but it was definitely not the last. And so I think that this is well articulated by the idea that what we did do well was get things from the first, second, and third waves of the systems thinking history. But what we are not prepared to do is kind of go into less technical, what's the word I'm looking for? We're looking for trying to understand how to move beyond our academic setting. And there's been a couple of areas in system dynamics modeling where that's really been shown to be important. And there's some emerging approaches that we would like to work into incorporating into this approach in future that can help us do that. And this is particularly important with working for community partners that these other tools are not going to speak to in the same way. And so we're exploring two areas: immersive systemic knowing that really embraces experiential, presentational, and practical ways of knowing, and then ideas about how to just talk about systems thinking and make it accessible and useful and for everyone, and what we need to change about system thinking approaches in order to do that. And with that, I will stop and take any questions if we have time. Thank you. I see a lot in the chat.
Thank you so much, Alex. That was so helpful and gave such a good overview of everything. That was really easy to understand from somebody who doesn't know what you're talking about. So yeah, thank you so much for providing some accessibility with that presentation.
Oh, I'm glad. I could do a whole nother one on like getting deeper into some of the things that we hypothesized and, you know, where we want to go next. But yeah, this was at least some of it. Hopefully it was useful for folks.
Thanks. Do folks have questions for Alex? Really?
Sure, super cool process. I know I've kind of chatted with you about it before and how it was developed. And I think at some point you were talking about writing it up. I think that process is also a really important part about how everything unfolded. Do you have thoughts about like how you might modify or share that process for helping others think through thoughts in different watersheds?
Yes. So, well, it is written up now. It's in review somewhere in the academic ether. So we'll share with the full team when it gets revised, hopefully, and accepted, hopefully. And it gets a lot more into the details of these tools. So I hope that that will be a great resource. And I'm happy to share the manuscript as it stands now before revisions with anyone who's interested in it. It has the appendices to defeat all other appendices because the manuscript necessarily had to focus more on like the framework as I presented it today, but all the details of the tools we used and the kind of nitty-gritty, including the code to do the structural analysis and whatnot, are available and have a long appendix that I hope somebody reads one day, or I'm going to be really sad. Yeah, Philip.
Hi, thank you. I had a quick question about how you guys separated endogenous and exogenous with your elements. Can you talk just briefly more about that?
Yeah, let me pull up. There's a really nice table that I think is worth sharing. What is going on? Oh. So the folks who developed this structural analysis based on, I'm just going to say in a kind of wishy-washy way, systems thinking theory kind of determined those category names, but they're pretty intuitive. Let me pull up my appendix because I think that the figure that can be a little overwhelming to show, but I think is really useful is this one. So this is based on those survey results of the research team. These are all the influences and dependencies of those course scale factors that went into the course scale model that you see labeled here. And they're the level of influence they have on other variables versus the level of dependence that they have on each other is what is plotted here. And so then the categories that then are, you know, how they function in the system are based on their placement on this plot. So there's a bunch of interesting stuff here, but like, for example, this quadrat where there's really low influence and really low, or sorry, I should say like this quadrat where there's really high influence but really low dependence is a great example of an exogenous factor because it's conditioning the system from the outside, but the system doesn't affect it very much. So you can see in the scope and scale of our project, this is weather and climate was considered more of an exogenous factor. So ones that are extremely depending and as well as influence would be those core endogenous ones. And then ones that are more endogenous are, but not so core to the system are these depending ones. Does that answer your question? Awesome. Somebody looked in my appendix. It's been a good day. I'll call it a win. I'll just end by, I didn't have time to mention Marisol, who's another student here in the TN, is really working on how to get those less quantitative stock and flow pieces into the framework. And so we're really excited about her work because that is a major area in systems thinking approaches that continues to need development. That's going to be, I think, really important for the Transformation Network's use of these tools. Great.
Great. Well, thank you so much, Alex. It's so great to hear what you're doing. And oh, I think I might have frozen. Yeah, and so everyone, we are going to continue having these speaker series in the fall, and so yeah, let us know if there's anything specific that you'd like to learn more about, if there's anything that you would like us to focus on, or folks that you have been collaborating with that you would like to include their voices in these sessions. This is really an opportunity for the TN network to come together and sort of help lead these as well. So please give us your feedback. Let us know what's working, what you'd like to focus on more of as we continue with this year. And thank you all so much for joining us today.
Yep, we have one more talk coming up on April 24th too from Yolanda Lin in the spring series. So I just put the flyer in the chat. Thank you, Alex, and thanks everyone for joining.